everyone, welcome to this video. Today, I would like to solve two problems that I found over on Brilliant.org, or as I call them, two brilliant problems. Sorry for the unoriginality of this video's title, but I'm sorry, I had to do it. So, let's take a look at the two problems. The first problem is we have a real alpha satisfying the following two equations, and we want to find out this quantity right here in terms of n and n. And for the second problem, we have a vector y being equal to this, the following matrix raised to the 20.1 power multiplied by this vector, and we want to find the last digit of the magnitude of y. So, I encourage you to pause the video, try the problems out for yourself, and see if you got the right answer. So, let's start with the first problem. I would first like to rewrite m cubed and n cubed in a single fraction instead of like two things being subtracted together. So, m cubed, let me just rewrite that 3, will be, this sine alpha will be sine squared alpha over sine alpha, which means combining the two we'll get 1 minus sine squared alpha over sine alpha, but 1 minus sine squared is simply cosine squared by the fundamental theorem of trigonometry, so this is cosine squared of alpha over sine of alpha, and n cubed, I was about to write an n again, will be equal to 1 minus cosine squared alpha over cosine alpha, and this will be equal to sine squared alpha over cosine alpha. Okay, I'll rewrite n over cosine alpha. But then, we don't want n cubed and n cubed, we want n squared and n squared. So, n squared will be raising both sides to the 2/3 power. We get that n squared will be cosine to the 4/3 of alpha over sine to the 2/3 of alpha. Similarly, right here, we can do n squared being equal to sine to the 4/3 of alpha over cosine to the 2/3 of alpha. Now, we'll multiply those two together. So, let's see. N squared will be equal to, okay, here we have sine to the 4/3 in the numerator and sine to the 2/3 in the denominator, so they will just become sine to the 2/3 of alpha by subtracting exponents. Doing the same thing for the cosine, we get that cosine 4/3 over cosine 2/3 will be cosine to the 2/3 of alpha, and then n squared plus n squared will be equal to, I'll just write this again, cosine to the 4/3 of alpha over sine 2/3 alpha plus sine 4/3 of alpha over cosine 2/3 of alpha. We'll combine everything in the common denominator, which will be sine 2/3 of alpha times cosine 2/3 of alpha. Okay, and now cosine to the 4/3 times cosine to the 2/3, adding exponents, we get cosine to the 6/3, which is cosine squared, so cosine squared of alpha, plus doing the same thing with the sines, we get this will be equal to sine squared of alpha, but then cosine squared plus sine squared is simply 1, so this will be 1 over sine to the 2/3 alpha cosine to the 2/3 alpha. Well, these two are reciprocals of each other, which means that multiplying the two, n squared times n squared plus n squared, will be equal to 1. For any real value of alpha, this thing right here will be equal to 1. That's amazing. So, this is an answer of 1. And I'll erase this board and we can start solving the second problem. Okay, for the second problem, this matrix is raised to a really large exponent, and that's pretty nasty, so let's see how we can simplify this. First of all, that matrix right here looks a lot like a rotation matrix, so let's investigate that further. So, 2 minus that this will be equal to 1/2 minus square root of 3 over 2, square root of 3 over 2, 1/2. But this is exactly of the form cosine theta minus sine theta, cosine theta. If our theta is equal to pi over 3. Yeah, pi over 3. So this is cosine pi over 3 minus sine pi over 3, sine pi over 3, and cosine pi over 3. So this matrix to the 2021, if we add the exponent, we'll simply get 4 to the 2021, which is a scalar, so it can be disregarded for now, times cosine times this matrix to the 2021. But now, this matrix is multiplied by a vector, which means that this is a rotation matrix, and it's raised to the power 2021. So it represents a rotation, 2021 consecutive rotations of pi over 3 radians counterclockwise about the origin. But eventually, after a few rotations, we'll get back to where we started after a period of 2 pi. So pi over 3 fits 6 times into 2 pi, which means that every 6 times we rotate, we'll get back to where we started. So raising this matrix to the 2021 is basically the same thing as raising this matrix to the 2021 mod 5. So this is the same thing as the matrix. I'll rewrite 4 to the 2021 as 2 to the 4042 because it will be useful later. And then this will become a 5 because it's 2021 mod 6, which is 5. And then 5 rotations of pi over 3 counterclockwise is nothing but 1 rotation of 5 pi over 3. So this is cosine 5 pi over 3, negative sine 5 pi over 3, sine 5 pi over 3, cosine 5 pi over 3. But now, cosine of 5 pi over 3 is 1/2, so this will be 1/2, this will be 1/2. Sine 5 pi over 3 will be negative square root of 3 over 2. Negative square root of 3 over 2, square root of 3 over 2, like this. So now, we can plug this back in and we can finish this problem. So, our vector y will be 2 to the 4041 because the 1/2, if we factor it out, it will multiply with this scalar, so subtract the exponents and everything, we get 2 to the 4041 times the matrix 1 square root of 3 minus square root of 3, 1, multiplied by the vector 2 over square root of 5, 1 over square root of 5. And now we can multiply this matrix and this vector together, so this will be 2 to the 4041 times, well, here we'll get 2 over square root of 5 plus 2 over square root of 5, so this will be 2 plus square root of 3 over square root of 5. Next, multiplying this and this together, we'll get negative 2 root 3 over root 5, and then plus 1 over root 5, so 1 minus 2 root 3 over root 5. And for the measure, we'll bring that scalar inside our vector, so 2 to the 4041 times 2 plus root 3 over root 5, 2 to the 4041, 1 minus 2 root 3 over root 5. Okay, now we're ready to find the magnitude of y. So, here we have 2 to the 4041 squared times this square plus 2 to the 4041 squared times this square, which means we can factor the 2 to the 4041 squared out of the square root. So, the magnitude of y, hold Well, let me try and find a pencil that writes better. So this will be 2 to the 41 times the square root of, well, everything will be over 5 because square root of 5 squared is 5, the square roots cancel out. And then 2 plus root 3 quantity squared will be 7 plus 4 squared of 3. And then 1 minus 2 root 3 squared will be 13 minus 4 squared of 3. But then the 4 squared of 3 will cancel out. 7 plus 13 is 20. 20 divided by 5 is 4. Square root of 4 is 2. So multiplying that by 2 to the 41, we get this will be 2 to the 42. So now we only want to find the last digit of 2 to the 42. So let me just rewrite this. Last digit of 2 to the 42 is equal to, okay. So let's start analyzing the first few powers of 2 and see if we can find any patterns. So let's make a table here. So n 2 to the n mod 10. So 2 to the 1 will be 2, 4, 3, 8. 4 it will be 16, which ends in a 6. 5, 2, 6, 4, 7, 8, 8, 6. Now the pattern repeats. So we can see that 2 to some 4k plus 1, where k is an integer, a positive integer, will be congruent to 2 mod 10. 2 to the 4k plus 2, because it's an even number which is not a multiple of 4, will be congruent to 4 mod 10. 2 to the 4k plus 3 will be congruent to 8 mod 10. And 2 to the 4k will be congruent to 6 mod 10. So we can have 4 possibilities. 4k plus 1, 4k plus 2, 4k plus 3, 4k. So 4042 falls in the 4k plus 2 category because it is 4 times 1010 and then you add 2. So the last digit of this will be